Hello everyone. Uh, Today we'll look at support vector machines, its geometric intuition, and as well as mathematical derivation. Support vector machines is a technique which can be used for both classification and regression depending on the problem statement. Now, the geometric intuition behind support vector machines is, suppose we have a set of positive points and negative points which are distributed like this. Now, what SVM does is it will try to find a hyperplane pi, which will make sure the positive and negative points are farther, like as far as possible. Now, uh, and this and the plane parallel to the pi, that is pi plus, what it does is both pi plus and pi minus, these are the planes which are close to the positive and the negative points. Now, and the plane pi plus is found such a way that it passes through one of the positive points and which is parallel to pi, and plane pi minus passes through a negative point, one or two negative points, and which is parallel to the pi. The distance between pi plus and pi minus, this distance is called as margin. Let me write that again, margin. So essentially what support vector machines try to do is it tries to maximize the margin. By maximizing the margin, the bunch of positive and negative points are as far as possible from the plane pi. Yeah. Now, equation of pi can be written as W transpose xi plus b equals to 0. And pi plus, it is W transpose xi plus b equals to 1. And pi minus equals to W transpose xi plus b equals to minus 1. Like these are the equations of hyperplane, respective hyperplanes. Now, the margin can be defined as a distance between pi plus and pi minus, right? That distance is nothing but 2 pi L2 norm of W. And how this can be derived is, um, let me increase my notes. Now, how this can be derived is, um, like consider we have two equations of line, ax plus by plus c1 equals to 0 and ax plus by plus c2 equals to 0. Then distance between lines is given as, distance between lines, this is can be found by modulus of absolute value of c2 minus c1 by square root of a square plus b square. I'll attach a link for derivation of this equation. Now, using this principle, we can find the distance between pi plus and pi minus distance is absolute value of b plus 1 minus b minus 1 by L2 norm. That is nothing but 2 by L2 norm of W. So the optimization problem for SVMs becomes like we have to maximize the margin, right? So the optimization problem becomes argmax of, we have to find W and B for which we can maximize 2 by, yeah, and this can be rewritten as argmin of, we have to find W and B for which this can be minimized. Now this is called as hard margin SVM. Why it is called as hard margin SVM is, as you can see from the data points here, it assumes the points are linearly separable. Like there are no positive points between the margin or on the negative side. Same with the negative points, they are not on the positive side or between the margin. So hence it is called as an hard margin SVM. Couple of them are within the margin and one is on the negative side. Now it is difficult to linearly separate these data points. So we can say that there's some error present in this case. Now how to measure that? So for like as we know, the equation of the plane is W transpose xi plus b equals to 0, and yi can be -1 or +1. So for the correct classification of data points, the product yi into W transpose xi plus b should be greater than or equals to 1. Be it negative or positive data point, this product should be greater than or equals to 1. And if there is any misclassification, then this product will be less than 1. So using this as our basis, we can find for point A, this is like we know this distance is called as margin, right? Now this is this side of pi. So and it's between pi and pi minus. So we can say uh, this product yi into W transpose xi plus b is equals to minus 0.5, because like we know this plus 1, 1 and minus 1, right? So as it's in between pi and pi minus, let's assume this distance from pi is like 0.5. So, and it's in the opposite direction of the correct hyperplane. So this can be rewritten as yi into W transpose xi plus b equals to 1 minus 1.5, right? Similarly for point B, this one yi into W transpose xi plus b, this is say 0.5. Now this can be written as 1 minus 0.5. And for point C, which is on the negative side of the hyperplane, now we know this distance is equals to 2, and as let's assume this distance from the pi minus to here is 0.5. So this becomes yi into W transpose xi plus b equals to minus say sorry, this can be say minus 1.5, 1 minus 2.5. So as you can see, there's some value, like some positive value here. And let's generalize this. If we generalize this, this equation can be written as yi into W transpose xi plus b equals to 1 minus zeta I. So for correct classification of data points, my zeta I equals to 0. For incorrect classifications, my zeta I will be greater than 0. Now what happens, our optimization problem we saw, we have to find W and B which can minimize my margin here. So similarly, uh, excuse me, if we add this error term, it becomes our new optimization problem becomes we have to find an optimal value of W and B where we will minimize this end C times 1 by n summation of I equals to 1 to n zeta I, and this can be interpreted as loss term, and this can be interpreted as our regularization term of for SVM.